Okay, so we are at the beginning of Unit 4, and we are starting to talk about thermodynamics. So thermodynamics is a topic that's important, and it doesn't usually get a lot of emphasis in Chem 1. So this is going to be new for a lot of you. So first off, some definitions. The first thing we have to talk about is something that we call the system. The system is usually a container. It could be the physical process that's going on, like salt being dissolved in water. That could be the system, salt dissolving. Could be a chemical process. That would be a chemical reaction going on. It's a very generic term. And then the surroundings, which would really refer to the rest of the universe. So if we were going to do a thermodynamics lab in our classroom, the system would be the reaction itself, and the surroundings could be, if it's going on in water, or the surroundings could be the entire room. So these are very general terms. And the idea of thermodynamics is studying the movement of energy between the system and the surroundings. And at the bottom here, we have a very generic picture. The system and the surroundings, they're two areas that are touching, but they're separate systems. So before we go too much farther, go and look at the PDF of these notes. You'll notice there's really not a whole lot for you to write until the very end of this video. With that being said, if you want to take notes on a blank piece of paper, that's fine. So here we're looking at three different types of systems, and we're looking at, can matter move back and forth between the system and surroundings, and can energy move back and forth between the system and the surroundings. So the first type, we have an open system. And an open system, matter can move back and forth. It could be in the system, and then it goes into the surroundings, and it could come back. There's matter in, matter out. And the same with energy. The system can lose energy, the system can gain energy, energy can go back and forth. And an example of an open system would be something like a cup full of water or a cup of coffee. It's an open system. If you knock it over, matter will leave the system and enter the surroundings. Same thing with energy. If it's hot coffee, it is constantly losing its heat to the surroundings, and so both matter and energy could leave a cup, which is an open system. Second thing we have is a closed system. And a closed system, in a closed system, matter is confined to the system. The matter cannot get out. Matter from the surroundings cannot get in. A good example of this is a water bottle with a lid, just a cheap plastic water bottle. So the lid is on it. If you knock it over, the water inside of it will not leave the system. It's confined to the water bottle. If you dropped it, you're not in danger of other materials getting into the water bottle. But energy can move back and forth through the plastic walls of this water bottle. So if this water was really cold at the start of the day and you're outside on a hot day, there's energy moving from the hot air into your water, and over the course of the day, your water warms up. And this is an example of how a closed system can exchange energy. Your last type is an isolated system. And in an isolated system, matter cannot move back and forth. There's no matter out. There's no matter coming in. Same with energy. There's no energy getting out of the system. There's no energy coming into the system. And an example of this could be like an insulated thermos with a lid. if you have some coffee and it's cold outside and you want this coffee to stay hot for a long time, you would put it in some sort of an insulated thermos and it might stay hot for 3 hours, 6 hours, 24 hours. It'd be a lot longer than a cup or just a regular coffee mug. With that being said, put an asterisk here. This is not quite an isolated system because energy still gets out, it's just a lot slower. So if you put hot coffee in this thermos and you come back in 12 hours, it might still be warm, but it's not going to be hot like it was originally. And so this is as close as we can get. This is as close as we can get to an isolated system, but it's not a perfect isolated system. Here I have some pictures that represent this differently, and the green arrows represent matter, and the red arrows represent energy. And so if you look at the open system, it's got matter coming in and out, it's got energy coming in and out. So there's nothing keeping anything inside, there's nothing keeping anything out. It's a pretty open exchange of matter and energy. By the way, this slide is not in your notes. You can draw it if you want. Then move on to a closed system, and what you see is that matter cannot get into the system, and matter is not getting out of the system. So as far as matter is concerned, it is stuck inside or outside of the system. But we still have energy that can easily pass back and forth. The third type was the isolated system, and you see there's no matter getting in, there's no matter getting out. Same thing with the energy. There's no energy getting in, and there's no energy getting out. So defining another term, the internal energy, and the symbol for this is a capital E, and it has INT. INT is not always there. It could just be capital E, the energy. So the internal energy of a system is the sum of all the kinetic energy and all of the potential energy. The kinetic energy, which is the movement of the particles, and it's pretty directly related with temperature. And the potential energy comes from the attractions between the various particles. So potential energy tends to be more like chemical energy. So we're coming up to the first law of thermodynamics. And the first law of thermodynamics is specifically talking about an isolated system. In an isolated system. Remember, that's the one where if we go back, it was here. There's no matter getting in, no matter getting out. Same with energy, nothing in or out. So in an isolated system, the change in the internal energy of a system is conserved, meaning it's constant. It's not going to change. So what this first law of thermodynamics says is that in this isolated system, energy can be converted from one form to another. So it could go from kinetic to potential, it could go from potential to kinetic. But the total energy of the system is not going to increase and it's not going to decrease. The internal energy of this isolated system is constant. There's a formula for the internal energy of the system, or in this case, with the delta, it is the change in internal energy of a system. So delta E equals Q, which is the heat flow, plus W, which is work. So let's look at these symbols individually. We already talked about delta E internal. So let's talk about heat. Heat is represented by the symbol Q, And heat flows between the system and surroundings in a specific way. It specifically flows from a place with a higher temperature to a place with a lower temperature. And it has a formula, Q, which is the heat flow, equals M, which is the mass, times C, which is the specific heat that goes for whatever substance you're talking about. C will be different. And delta T, which is the change in temperature. So Q equals MC delta T. Heat flow equals the mass times the specific heat of the substance times the change in temperature. And then we have work, which is W. This is a lowercase w. This is energy that comes from the expansion or compression of a gas. And in the examples that we work in this unit, we're specifically talking about, usually the idea is in a piston. And a piston is basically a syringe where you have this cylinder and you can push the plunger and decrease the volume, or you can pull the plunger and increase the volume. You've seen these before in Chem 1, and next time I see you, if you need a visual, I'll be happy to get one out. There's a formula for the work. So the work equals negative P, which is the pressure, times delta V, which is the change in volume. Work equals negative pressure times the change in volume. So you'll notice here that delta V means the volume is changing, but P does not have a delta. This is just the pressure. So this is going to remain a constant. Pressure, it's the volume that's going to change. Since this cylinder can change its volume, it will. And it will change its volume to account for the pressure. The pressure wants to remain constant. So in this next picture, it's showing 4 different things, and it's heat and work. And so this is not necessarily like heat flows in, heat flows out. This is showing 4 completely separate processes. So if you look just at the heat at the top, heat could be flowing in, heat could be flowing out. The reason I drew it like this is because in your notes, it's all drawn in the same picture. So let's first take a look. Here is the system. It has an internal energy, and you can see it's got 3 walls that are solid, and then this one can move up and down, just like a piston or a syringe, whatever you want to call it. Piston is the chemistry term. So first, let's look at the heat flowing in. If the heat is flowing into the system, so it's in the surroundings and then it flows into the system, Q is going to be greater than 0. Heat coming in. Q greater than 0, and this process is called endothermic, and I underline endo. Endo, it sounds like into, endothermic, heat flowing into the system. The opposite process is if heat flows out of the system. Heat is flowing from the system to the surroundings. You have this Q, which is less than 0, and it is exothermic process. And so I always think exo, exit, heat is leaving the system. Your other possibility, remember your change in internal energy could also result from work. So if work is being done on the system, it's greater than 0. So this is like compression. I am pushing down on this plunger and I am purposely decreasing the volume. I am pushing it in. And so that's work. And then work coming out of the system, or In other words, the system is doing the work. The system, if I push the plunger in, I'm doing work on the system. If I let go on the plunger, the system is going to push it back out. It is going to do some work in order to get it to expand. And in this case, the work is less than 0. So these 4 ideas we will talk about more than just in this video. But it's important that you get these 4 concepts down so that way it makes the rest of the unit easier. So this is something, these 4 processes, you're going to need to remember what's going on and is it greater than or less than 0. Heat coming in, the system's energy is increasing, that's why Q is greater than 0, and it's endothermic. If the heat is flowing out, the system is losing energy, and that's why Q is less than 0, and it's exothermic. And now we get to the bottom of the first page, and this is our first example. So let me read it to you. It says a 20.0 gram sample of argon gas in a cylinder with a piston at 30 degrees Celsius. And so you can see up here I've got the mass of my argon gas, and it says it is initially at a temperature of 30 degrees Celsius. It says heat flows into the cylinder and increases the temperature to 40 degrees Celsius. And so here's my new temperature. And you'll notice that I have labeled these T1 and T2. T1 is the initial temperature. T2 is the next temperature or the final temperature. It says the cylinder expands against a constant pressure. Remember that P is constant. 95.5 kilopascals. It is expanding from 21.5 liters, so that's my initial volume, from 21.5 to 23.5 liters, and this is my new volume, final volume. By how much has the internal energy of the system changed? So what's the change in the internal energy? We are looking for delta E internal. And then there's a couple other notes. It says that argon has a specific heat of 0.52 joules per gram degree Celsius. And it also tells us that 1 joule equals 1 liter times 1 kilopascal. So we're going to use the formulas for internal energy that we just learned. So here's what we want to know. What is the change in the internal energy? And we have a formula on this page. We know that it is Q plus W, the heat flow plus the work. We have a lot of information here, and we need to sort it out. So let's do these individually, and then we'll plug them back in. So let's look for Q, and its formula is MC delta T. So for this one, we have a mass of 20.0 grams, and that's argon gas. This is one of the few places in chemistry where we're not going to change it to moles, because if you look, this specific heat, which comes next, is 0.52 joules per gram degree Celsius, and these grams are going to cancel out just like that. And then the next thing is delta T. So we're looking for the change in the temperature. And in order for this, let's pause, and I have another slide to show you. And maybe if you have a blank piece of paper, if you've been taking notes, you can write this down. So here's what we're looking at. I have two thermometers that I drew here. One is in terms of Kelvin, one is in terms of degrees Celsius. Now there's a lot of overlap. If you have a temperature in Kelvin, it also has a temperature in Celsius. The difference is how are we expressing it, how are we writing it, how are we measuring it. So let's look at a few temperatures that we know. So on the Celsius scale, this line right here. So the freezing point of water, the freezing point of pure water. On the Celsius scale, we know that the freezing point of pure water is 0 degrees Celsius. And we also know the boiling point of pure water is 100 degrees Celsius. Now it's possible to have a temperature colder than 0 Celsius, and it's possible to have a temperature that is higher than 0 degrees Celsius. There is a lowest possible temperature in the universe, and that is absolute 0. And as far as Kelvin goes, that is 0 Kelvin. It's not degrees Kelvin, it's just 0 Kelvin. So here's some values that I know. And so I'm pretty sure this is on your AP formula sheet, the conversion between Kelvin and Celsius. Kelvin equals degrees Celsius plus 273. So if I want to know the freezing point of pure water, it is degrees Celsius, which is 0, plus 273, which means the temperature here is 273 Kelvin. If I want to know the boiling point of pure water, it's the degrees Celsius, which is 100, plus 273. So it's 373 Kelvin. If I want to know absolute 0 in terms of the Celsius scale, so we'd be looking for this degrees Celsius. And so rearrange your formula. You have degrees Celsius is Kelvin minus 273. So 0 Kelvin minus 273, negative 273 degrees Celsius. Now you'll notice that the intervals are the same. From this point to this point is 100 degrees Celsius. And from the same point here to here, that is 100 Kelvin. And so the scale is the same. The only difference is where is the 0 marker? And so now we're going to go to our specific conditions for this question. So the initial temperature is 30 degrees Celsius. So let's say here T1 equals 30 degrees Celsius. And the second temperature is 40 degrees Celsius. If I want to know the delta T of these two terms, delta T equals T2 minus T1. And so delta T is 40 degrees Celsius minus 30 degrees Celsius. And the change in temperature is 10 degrees Celsius. Or you could say positive 10 degrees Celsius. It went up by 10. The plus is not necessary here, but it increased by 10 degrees Celsius. There are some places in chemistry where you have to change degrees Celsius to Kelvin. And this is not one of them. You could if you want, but it's not really necessary. So if you look at our T1 in terms of Kelvin, so 30 plus 273, 303 Kelvin. And your final temperature, 40 degrees Celsius plus 273, 313 Kelvin. And so if you do the change in temperature for this one, it is 313 minus 303, and the delta T here is 10 Kelvin. So it increased by 10 degrees Celsius. It also increased by 10 Kelvin. There is no need for us to change Celsius to Kelvin in this question, because when you're looking for a delta T, the number is the same. The only thing that changes is the units. So let's look back over here. Delta T was the final temperature minus the initial temperature. And of course the Celsius, which is 10 degrees Celsius, and the Celsius cancels. And so we get a number which is 104 joules, and it's actually positive 104. So what does a positive value for Q mean? Let's flip back here. Q greater than 0, this is endothermic, which means that heat is flowing in. Heat is flowing in because Q is less than 0. Excuse me. Greater than 0. Q is greater than 0. So we know part of this. We know what Q is. And so now we want to find W, which is the work. And the formula here, work equals negative pressure times the change in volume. And so we have the numbers here. Let's plug them in. Negative pressure is 95.5 kilopascals. And volume is, delta V is 23.5 liters minus 21.5 liters. And so we end up with, let's do one more thing. So you notice this is kilopascals and liters. This is joules, and we have a conversion here. So let's go ahead and put our conversion in. 1 kPa times liter is 1 joule. So kPa's will cancel, liters will cancel, and it'll give us joules. And this comes out to negative 191 joules. Let's flip back to our chart here. So work is less than 0, which means the system is expanding. The system is doing work. And this is, work is less than 0. Okay, so all of that to find delta E. Q plus W. Q is 104. W is 191. And so negative 87 joules. And so what this means, the system loses, that's what the negative means, loses 87 joules of energy to the surroundings.